Welcome back. We were discussing continuous time Markov chains. Today we will continue to discuss CTMCs and proceed to discuss their steady state behavior. Before that, I would like to begin with a recap of what we have studied so far. CTMCs are characterized by an embedded Markov chain, okay, embedded DTMC, let us say denoted by xn, which we assume to be reducible and without having any self transitions, and holding times exponentially distributed with parameter some nu I when the embedded DTMC is in state I. Alright. So, this is what a CTMC is. So, the DTMC has some, the embedded DTMC has some transition probabilities Pij, alright, and it is some generic possibly countably infinite state Markov chain. Okay. Now, there are many ways of notating a DTMC, a CTMC. One is to draw out. So, let me just take maybe I should take an example of the MM1Q, which is a continuous time Markov process. You have seen this before. Let me just use this example to show you how to variously notate graphically a CTMC, right. The one is to draw out the embedded DTMC, right, which we already did. So, this is the embedded DTMC. You always go to from 0 to 1, and you know these are mu over mu plus lambda and lambda over and so on. Right, and so this is just the underlying the embedded Markov chain, embedded DTMC. Now, for the CTMC, you can put on top of each of these states the holding times, right, or the holding rates, okay, the new i's, all right. So, which maybe I will use in a different color. So, on state 0, how long do you stay in state 0? You are basically expecting an arrival, right. So, the rate at which this the new 0, right, the rate at which you get out of state 0 is lambda, and for the all other states, right, the holding times are, so here nu 2 would be lambda plus mu, right, the nu 1 would be lambda plus mu, nu 0 is lambda, right, nu 3 will be equal to lambda plus mu and so on. So, this is one way of notating the CTMC corresponding to the MM1Q, all right. This is one kind of notation. Another kind of notation is to use the, so here you are, the notation 1 you are using, so you are drawing out the embedded DTMC plus holding rates, holding times or holding rates, right. So, you are explicitly writing that out. In the second case, you can use a time sampled DTMC. You basically divide time into little delta intervals, okay, and you look at the transition probability from time k delta to time k plus 1 delta, all right. And what you will see is that you will have, for example, in state 0, you have a forward going probability of lambda delta plus little o delta, right, and holding probability the self transition probability of 1 minus lambda delta plus little o delta, all right. And in state 1 again, so all the forward going probabilities are lambda delta plus little o delta, right, and all the reverse probabilities are mu delta plus little o delta, and so on, all right, dot. And of course, in all these states you will have a self transition of probability 1 minus lambda delta minus mu delta plus little o delta, right. All these you will have ditto, right. So, this is the time sampled DTMC. So, and this approximates the CTMC as this delta becomes really small, right. As little delta goes to 0, this little o delta term will be very small, and you can just look at the transition, forward transition probability as just lambda delta, reverse transition probability as mu delta. Okay. Of course, please note that there will also be these sort of, these transitions are possible, but they all have probability little o delta, right, and as delta goes to 0, these 2 jumps and 3 jumps are ignored, all right, which is why I have not drawn it in the picture. Okay. They are there, but for delta small I am going to just ignore it, okay, these double jumps and triple jumps, all right. So, this is the second notation. Okay. Here you are basically drawing out, looking at little delta intervals and looking at the way the Markov chain jumps in these little delta intervals. Okay. This is a time sample DTMC approximation to the CTMC, and the approximation is increasingly good as delta goes to 0. There is another third way of looking at it, which is in terms of QIJs, which we defined yesterday. QIJ as we defined yesterday is Pij times nu I, all right. So, Qij can be interpreted as the rate of transitions from I to j, all right. So, you can view whenever you are in state I, you can view all these Qij exponentials as competing with each other, all right. One of these Qij, they are independent exponentials. So, it is like racing Poisson processes, racing exponentials, and the probability that a particular exponential j, say the Qik exponential, will win with probability Qik over sum over Qij, which is Qik over nu I, which is Pik, right. So, the probability of going from I to k will be Pik as you would want, okay, and the holding times will be exponential with parameter nu I, okay. So, this you can show. So, you can actually draw out between states I and j, instead of drawing probabilities, you can actually draw the rates, right. So, in previous two notations, what we drew out was a DTMC, right. We, in the first case, we drew out the DTMC which is embedded, and then in blue we wrote out the holding rates. In the second case, we drew the DTMC which is the time sample DTMC. In the third case, I am saying that we can just draw out not a DTMC, but a CTMC with all the transition rates, okay. Now, what I am going to draw is not discrete time, it is a continuous time process, okay. But nevertheless, you can look at the state transitions, you can just do this lambda mu, lambda mu, that is it, okay. So, here you are just notating the Qijs, right. So, this is the third way of drawing a CTMC, and these three you can go from any one to the other easily. This is just an example, you can do it for any CTMC, right. So, MM1 is probably the most widely encountered CTMC. So, I am just drawing that out. Now, remember that, so I am going to get back to the question of the steady state behavior, okay, which is very important aspect of CTMCs. Please remember that for the embedded Markov chain, we already derived the pi i's, right. So, assume that the embedded Markov chain embedded DTMC is irreducible and positive recurrent, okay. then you can derive pi i's, right. We can then solve for pi i's. How will you do it? We can then solve for pi i's from pi p equals pi, right, and sum over pi I equal to 1, equal to 1, right. So, we did that already for the embedded DTMC of the MM1Q, we already solved that, right. In the last lecture I indicated how the pi i's look. So, this pi i's, right, this pi i's, pi I denotes uh, the probability of transition into state I, okay, and it is not the fraction of time spent in state I by the CTMC. Okay. Pi I is the steady state probabilities of the embedded DTMC, all right. So, in the DTMC case, the fraction or the probability of transitions going into a state is the same as the fraction of time spent in that state. That is because for a DTMC each state you spend only 1 unit of time, right, but for a CTMC that is not true, you spend different amounts of times in different states depending on the holding times and holding rates nu I, right. So, while pi I denotes the fraction of transitions going into a state I for the CTMC, it does not denote the fraction of time spent in state I, all right. So, our consideration now is when you are talking about the steady state probabilities, how do you relate these pi i's, which is the fraction of transitions going to state I, to the fraction of time spent in state I. Okay. This is, so we are now going to discuss steady state probabilities for a CTMC. So, throughout I am going to assume that the embedded DTMC is irreducible and positive recurrent. Okay. Now, the question is, now we want to answer two questions. Under what conditions is there a set of probabilities? Let us now call them Pj, j belongs to S, with the property for a given starting state x not equal to I, Pj represents the fraction of time spent by the CTMC in state J, question mark. Okay. So, I am going to use, so I am looking for a set of probabilities Pj, I am calling them Pj to distinguish them from pi j, right. Pi j is the steady state probabilities of the embedded Markov chain, which represents the fraction of transitions going into state J. Pj represents the fraction of time spent by the CTMC in state J, okay, and I want to find, does there exist such a Pj, how is it related to pi j and all that. And also the second question I want to answer is that if the above probabilities Pj's do exist, do Pj satisfy Pj is equal to limit t tending to infinity probability of xt equals j given x naught is equal to I, x 0 is equal to I. Okay. So, this is, if you can view this as time average interpretation, and we are saying that the same Pj under some nice conditions which we have yet to discover, that this is an ensemble average or a steady state probability interpretation. Okay, the same Pj's, ideally we would like to have a Pj as the average fraction of time spent in stage J, and also the long term probability. If I start the process in CTMC in whatever state I want I, is there, does this Pj satisfy that as t tends to infinity, the probability of being in state J at time t as t tends to infinity is in fact Pj, right. We want to answer these questions. Okay. Again, there are a few ways to do this. We can, since we already know renewal processes, we can use the renewal process approach. Okay. So, that is probably the most straightforward way to see how these Pj's, why these Pj's exist in the first place and how they are related to the PyJ's, alright. In fact, what we will see, maybe I should give you the answer, right. So, if the so the answer is this, right. If the embedded DTMC is positive recurrent and irreducible, we are assuming that, and if sum over pi j over nu j, sum over j is finite, then Pj given by Pj is equal to pi j over nu j over sum over k pi k over nu k are indeed the steady state probabilities of the CTMC. Okay. So, this is I am just throwing the answer at you before we derive it. So, we need two things. Okay. We of course need that the DTMC be positive recurrent, otherwise you will not even find these pi j's, right. Suppose these pi j's are well defined and sum over pi j over nu j is finite, alright. Then these Pj's exist, Pj's defined like so, like here. Of course, these are very clearly probabilities, right, because they sum to 1. Notice that the denominator is assumed to be finite. So, Pj's are some probability distribution, right, over the states. In fact, these Pj's we will show are the steady state probabilities, also the time and also the average fraction of time spent in state J. Okay. So, this is what we want to show. Notice that this assumption is required. The sum over pi j over nu j is infinite, then even if the underlying DTMC, embedded DTMC is positive recurrent, then you will not find these Pj's, a probability distribution Pj will not exist, which corresponds to the fraction of time spent in state J or a steady state probability interpretation, right. Neither is possible. So, in fact, this sum over pi j over nu j, if it is infinite, that is it is a slightly pathological case. The intuitive way to think about it is that if pi j over nu j, sum over j pi j over nu j is infinite, then some of these nu j's are so small that the rate of the transitions in these states becomes so sluggish that the continuous time Markov chain actually does not move forward much, right. It just kind of although the embedded Markov chain keeps running in discrete time, the new j's are so small that the CTMC is so sluggish that it makes only finitely many transitions in infinitely many time at some in some at some intuitive level, right. So, you will not have the interpretation of steady state probabilities, but that is anyways it is a somewhat pathological case. All I am saying is that the sum over pi j over nu j should be finite for this steady state probability interpretation to even work, all right.